Now I'm going to talk to you about neutron porosity measurements, another group of measurements that we make which is vital to the understanding of a reservoir. We have one tool in particular which provides this measurement, and I'll take you through some of the details of that now. The tool I'm talking about is the compensated thermal neutron tool, CTN. This tool really makes one basic measurement, which is the neutron porosity measurement. Some of the larger tools also have an acoustic caliper built into them, but the primary measurement is the neutron porosity measurement. It comes in 3 different flavors. As you may already know, we typically present neutron porosity either in limestone units or in sandstone units. Very rarely we present them in dolomite units. Usually it's limestone or sandstone. So I'm going to explain to you the differences between those and how we get the measurement from the tool. On the right hand side you've got a picture of the tool with some cutaway showing the detectors inside. The way this works is we have a neutron source. This is a radioactive source that puts out neutrons that is screwed into the outside of the collar down here, and that radiates neutrons into the formation, which bounce around in the formation and eventually come back to the detectors, which can be then counted. We have 2 arrays of detectors. We have a near detector array and a far detector array. And by measuring the count rates in those detectors, we can calculate the porosity of the formation, and I'll show you how that actually works in just a minute. And up here, these ports are for the acoustic caliper. This is a 6 3/4 inch tool, and this is the acoustic caliper up here. There are 3 ports. I'll talk to you a little bit more about acoustic caliper measurements later in this presentation. Now, it's useful to think about the life of a neutron when we're thinking about how this tool works. Remember I said that the neutron source emits neutrons into the formation. Those neutrons come from the source with some high energy. They're not all exactly the same, but they all have high energy. And then as soon as they leave the source, they start colliding with the surrounding materials. That can be the borehole, the formation, the rocks, the fluids in the rocks, the tool itself. All of the materials immediately around the source are collided with by the neutrons. And every time they collide, they lose some energy. So you can imagine that the energy that the neutron has diminishes. Every time it collides with an atom, it loses a little bit of energy. Eventually it gets down into this zone at the bottom here, which we call the thermal zone. The thermal zone is the zone where the energy of the neutron is similar to the energy of the atoms in the formation or in the surrounding materials. All atoms will have some energy due to their having some thermal energy associated with them. So they're all kind of vibrating with that thermal energy. And when the neutrons get down into that zone, they have a similar amount of energy to the atoms. They can occasionally actually pick up some energy, as shown here. If they collide in the right way with an atom, it can actually boost it slightly. But they will spend a long time, sometimes down here in the thermal zone, until they are finally captured. Certain atoms in the formation are good at capturing neutrons. So most neutrons, all neutrons that come out of the source, will eventually be captured, having made a series of collisions. Now, the important thing is that this thermal zone is the zone where our detectors are tuned to detect the neutrons. When they're up here with high energy, the detectors cannot detect them. The detectors are designed so that they're only going to pick up these relatively low energy thermal neutrons, and so we have to wait for them to be slowed down before they can be detected, but we don't want to wait too long, otherwise they'll be captured. So there's a balance to be had in our tool design, which I'll explain in a little while. So let's think a moment about the source and the neutrons that come from the source. Here we have the source. It's radiating neutrons in all directions. And as those neutrons are colliding with atoms in the surroundings, they get slowed down. And the plot is intended to show the concentration of thermalized neutrons around the source. So close to the source we don't get very many because most of them are still moving very fast. they haven't had many collisions and they haven't slowed down. As we move further away from the source, the neutrons have had more collisions, they've lost more energy until we reach a point here where there's a very high concentration of thermal neutrons. As we move further past that point, neutrons are tending to be captured, and not very many of them are still around by the time we get out to the edge of the cloud here. So by the time we get out here, most of them have been captured. So there's a kind of a sweet spot in the middle here where there's a high concentration of thermal neutrons, and that's where we choose to put our detectors in the tool. The source and the detectors, of course, are both in the tool, and we choose the spacing from the source to the near detector so that it falls roughly where we think the maximum number of thermal neutrons is going to be. We choose the position of the far detector so it's out nearer to the edge of the cloud. Now, the cloud is going to change in size based on the number of collisions and the types of atoms that the neutrons collide with. If you're in a formation where the surrounding elements are very good at stopping neutrons, you'd expect the cloud to be small because most of them get stopped within a short distance of leaving the source. In other formations with different elements around, you may expect them to get a bit further before they get thermalized, and so the cloud will be larger. Now, the main thing that drives that is the fluids in the formation. In fact, in particular, the hydrogen that's present in the fluids. Hydrogen is a very good stopper of neutrons. It slows them down very effectively. So the more hydrogen there is around, the smaller this cloud is going to be. So variations in the concentration of hydrogen result in variations in the size of this cloud. And the concentration of hydrogen is closely linked to the porosity because most of the hydrogen is present in the fluids. So as the porosity goes up and down, you'll see changes in the size of this cloud. With high porosity, the cloud is small. With low porosity, the cloud is large. And that's going to have an impact on the count rates that we see in our detectors. So by measuring the count rates, we can infer what the porosity is in the formation. So what we can do is in the laboratory, with some measurements and also with some modeling software, we can calculate a relationship between the near-far ratio, that's the ratio between the near and the far detector count rates, and the porosity of the surrounding formation. So we get a nice curve like this for each of the different tool types that we have. So all we have to do is measure the near-far ratio, and then from that, for each tool type, we can read off what the porosity is. Unfortunately, that's not the end of the story. If it was, then the neutron porosity measurement would be probably far more popular than it is. In practice, there's a lot more that we have to do to the measurement after this in order to produce something which is actually meaningful and useful. The issue is that the neutron porosity measurement is sensitive to other things besides just porosity. The main thing that we're looking for is hydrogen, and of that, the main source of hydrogen is in the formation fluids, which are in the pore spaces of the rock, which is the thing we're trying to measure. But hydrogen is also present in the borehole fluids, in the drilling mud that's in the hole around the tool. That's based on water or based on oil, contains a lot of hydrogen, and we need to compensate for that somehow. We also have to compensate for the rock matrix, the actual rock type that we're in. Some rock types are better at slowing down neutrons than others are, and so we have to take that into account when we're calculating porosity. We also have to take account of the amount of chlorine that we have present. Chlorine is a very good absorber of neutrons, and it's present in quite large quantities in a downhole environment. We have it in salt, sodium chloride, which is in the borehole, and also in naturally occurring salts, which are in the formation water. In both places, the chlorine is going to tend to reduce the number of neutrons present, and that would affect our measurement. The measurement's also sensitive to tool position. Whether the tool is centralized or off-center in the borehole makes a difference to the response, so we have to somehow make a correction for that. The measurement is also sensitive to both temperature and pressure, because both of those things have an impact on things like the density of the mud in the borehole, the behavior of the hydrogen atoms and other atoms that are present in the formation. Those change with temperature as well, and also pressure. So it's a very complicated situation with a lot of aspects to it that have to be taken into account before we can come up with a true measure of the formation porosity. So just to illustrate some of those points, here I have a chart that shows the first few elements of the periodic table, starting with hydrogen, of course. And on the vertical axis is the ability of those elements to slow down neutrons. The reason hydrogen is so good at slowing down neutrons is that the mass of a hydrogen atom is almost the same as the mass of a neutron. And so it's possible for almost all of the energy in a neutron to be lost to a hydrogen atom if it collides in the right way. Whereas with larger atoms, their tendency is more for the neutron to simply bounce off without losing so much energy. So hydrogen is very dominant, but we also find that there are other elements present which contribute to the neutron moderation. So for example, here we've got a case where we have some carbon, some oxygen and calcium present. That's what you'd expect to see in limestone. So if you're in a limestone formation made of calcium carbonate, you've got those three elements present. So those are, although they're not as good as hydrogen, they are going to contribute something towards the moderation of the neutrons. If we add some magnesium, now we're looking at a dolomite situation where some of the calcium has been replaced with magnesium to make dolomite. And again, that's going to make a contribution to the neutron moderation and affect the measurement. Similarly, in sandstone, we'll have silicon and oxygen. They will also contribute, but contribute differently from what we had in the limestone case or in the dolomite case. So again, we have to take this into account if we're going to correctly calculate our porosity. Now let's look at how good some of those elements are at capturing neutrons. These are the same elements that I showed before. This time I'm showing how good they are at capturing neutrons. I've already said that chlorine is our main capturing element in the downhole environment. These other two, fortunately, we don't see. Lithium is a rare element that doesn't show up much downhole, as is boron, which is extremely good at moderating neutrons. It's off the chart on this scale. That material is used in nuclear reactors to slow down nuclear reactions. In the downhole environment, it's all about the chlorine. Chlorine is present in sodium chloride, it's in the formation water, it's in the borehole fluids. And that is the main element that's going to have an impact on our neutron count downhole. So because of all these corrections that we have to apply, one of the things we do when we QC our data is to make sure that they've all been applied correctly. So what I've got here is a standard plot which shows all of the corrections and all the input parameters that have been used to correct our neutron porosity measurement. On the left-hand side, I've got the near and far detector average count rates. That's what you might regard as being the raw data that goes into this. On the right, or on this third track, I've got porosity, and there are multiple curves in here, and each curve represents one step in the correction process, and those are labeled up here. So for example, the red line, porosity 0, is the raw porosity that comes out of that ratio to porosity transform that I showed you a couple of slides ago. The first correction that's applied is for hole size, which is the blue dashed line, and then the next correction is offset, which is the tool position, and then we have corrections for mud weight, borehole salinity, formation salinity, formation fluid density, and something called an excavation effect, and finally a temperature correction. So each of those is shown as a separate curve, so you get a feel for how big a correction each one of those represents. And this example is fairly typical, where they're fairly closely stacked together. If you see one where there's a very large step or very large correction being applied, you might want to look at that because it may be erroneous. It's not normal to see such large corrections. Over here we've got, these are all limestone curves. Over here we've got sandstone and dolomite porosities. From the fourth step in the correction process, the processing splits into three. So we have the limestone curves, the dolomite curves, and the sandstone curves, 4, 5, and 6, and then the final porosity. So there's like 3 branches of porosity calculation from that point on. In the second track, I've got all of the inputs which are used in those calculations. So I've got an input for hole diameter, mud density, mud chlorides or salinity, formation water, salinity, temperature, pressure, and average offset, which is the position of the tool in the hole relative to the center, so how far off center it is. So you can see each of those is plotted as a curve. When you're QCing this data, it's important to look at this and to make sure that each of these values is reasonable and within the range that is expected, because any one of these being wrong is going to result in the final porosity being wrong. So here I have an example where something is wrong. What I'd like you to do is take a few moments to pause the video and to look at the log and see if you can work out what you think is wrong. Okay, so hopefully you've had a chance to look at the log, and you'll have noticed this large step between P6, porosity 6, and the final limestone porosity. We have an enormous difference between these two. This is caused by the temperature correction. This is the final step in the processing, is the temperature correction. So we look at the temperature input, and we can see this is on a 0 to 150 scale. So we're looking at about 120 Celsius or something like that, which doesn't sound completely unreasonable. It sounds about where we expect it to be. So what you can do in a case like this is to go and look at the live data. Rather than looking at a QC plot, get the data into Insight Plot Manager, and that has a function where you can hover your mouse over the track and you can see a digital display of what the actual temperature and other parameters are. And you can see from this one that we've got a value of 260 Celsius in here, which is way too high. The tool is only rated to work at 175, so for it to be 260 would be impossible. So this looks like it's a bad data entry. Someone's put the temperature in incorrectly, and what that's done is it's generated an enormous temperature correction, which is not realistic. So what we can do then is to go back into the data, back into Insight, make a correction, identify what the proper temperature should be, and then reprocess the data. And if we do that, we get a temperature which is more like about 75 rather than 260. And now we see a much, much smaller temperature correction. So that looks a lot more reasonable, and I think we can have a bit more confidence that that's a correct result. All right, so here's another example where we seem to have a problem of some kind. I'd like you to take a few seconds to look at this log and see if you can work out what's going wrong. Okay, hopefully you've had a chance to look at this. What this is a standard plot which displays the count rates from the detectors in the tool, and it also compares the real-time and memory porosity. This is a standard layout that we use for all the CTN QC. The first thing that strikes me is the difference between the real-time and the memory data over here. The porosity from the real-time, the red curve, is reading about 25 PU or something like that, whereas the memory data seems to be much higher. It's almost 60 PU, which is not realistic. Meanwhile, over here, we've got the count rates from the detectors. Now, on this track, we've got 6 trace labels, implying that we should be looking at 6 different count rates from 6 detectors, but in fact we're only seeing 2. We're seeing number 1 and number 2 are the only ones showing up. And over here, we seem to only have 1, 2, 3, and 4. We don't see 5 and 6. Now, this is a bit of a trick question because although some of our tools do have 6 detectors in the near and 6 detectors in the far, some of them don't. In fact, the more recently produced tools only have 2 near detectors and 4 far detectors. So this is just a case of the wrong template, really, the wrong plot template being used to display the data. But that doesn't account for what we're seeing. Just because there's fewer channels available or fewer detectors in the tool doesn't account for why the real-time and the memory are so different. The other thing that I notice on this plot is this spiky response on the far detector number 4. And in fact, if you look closely, that far detector number 4 is not visible over most of the log. It's not there. The black trace doesn't show up. It's only visible in this interval here. So what I did in this case was to replot the data to see if I could find where that black trace was going. And I replotted on a 0 to 1,000 count rate scale instead of 0 to 100. And now I'm seeing number 4, which is showing a very, very high count rate compared with the other 3, which are all down here now. So that says to me that we've got a failure in the number 4 detector, and that's causing a problem with the calculated porosity. The reason there's a difference between the real-time and the memory is that in real time, the tool itself has some logic which automatically excludes a bad detector from the processing. So the tool will be comparing the counts from the 4 detectors in the far bank. It will realize that number 4 is an outlier and it's very different from the others, and it will automatically exclude that detector from the calculation for real-time porosity. Now that does not happen in memory data processing. In memory data processing, it's up to the user, that's you, to decide whether a particular detector is good or bad, and there are controls within the insight processing which allow you to disable a bad detector if you think that's the case. So what's happening here is that the memory data is being processed using all the detectors, even though one of them is bad, whereas the real-time data, you're seeing the logic from the downhole tool throwing out this bad detector to just give you what is hopefully a good porosity value. So to fix this problem, what you can do is reprocess the memory data and disable far detector number 4 to exclude it from the processing. And what that does is then bring the memory data, which is the blue curve, in line with the real-time data. And that gives you some confidence now that the processing is correct.